morning. Yesterday, you did a lab looking at testing acids and bases to find out some of their properties. A property is a characteristic of something. For example, if you test an acid with litmus paper, what color will that litmus go? Okay, so red, or some people said pink. That's fine because the red litmus paper is kind of a pinky color. Versus blue, bases will go blue. Sometimes we call that the BB rule. What about reactivity with metals such as magnesium? Yes, acid reacts with metals, bases don't. That's a good thing, because we use a strong base known as sodium hydroxide to help us clean the inside of our ovens. If that reacted with metal, then when you came back in the morning to actually wipe the sprayed stuff out of your oven, you wouldn't have an oven. So it's a good thing it doesn't react with sodium hydroxide. What about conductivity? Yes, but distilled water is not. Did that throw you for a loop? Then how come if you drop a toaster into your bathtub, it can electrocute you? If distilled water is not conductive, it shouldn't matter.
The water that comes from our tap still has crap in it, like iron.
Ah, exactly. The stuff that comes into your bathtub is not 100% water. It's got other stuff like iron, or if you've added an essential oil or salt or bubbles, then other stuff is in there. So please don't drop a toaster into the bathtub. If you actually look at the warning label of a toaster, it will say don't drop it into the sink or the bathtub. Same thing with the hairdryer. You keep that away from the bathtub as well. Acids and bases have properties, and because of those properties, we can use them to do things for us. One of the nice things about using universal indicator as a tester for how acidic or basic something is that a universal indicator gives a color change from 1 to 14 on the pH scale. We have many types of indicators that we can use, but oftentimes they're only for a very narrow range. In Chemistry 30, we use something called phenolphthalein. And phenolphthalein only changes between a pH of 8 and 11. Less than an 8, it's clear. There's actually no color. It's only once it reaches a pH of 8 that it starts to turn a very, very faint pink color. And the more basic it is, the darker the pink it is. When you tested acids with the universal indicator, what color was it? Okay, it was red. Versus when you tested with the base, what color was the universal indicator? It was in the blue range. And around here, pH of 10, 11. Okay. In the second part of the lab, you had to start off with some acid in one part, a test tube, for example, and a base in another test tube. And then you combine them together, and you saw a color change. For some of you, the color change ended up right here. For some of you, the color change was in around here. For some of you, the color change was maybe in the tealy range. It depended on how much acid and how much base you added. Why is the final pH somewhere in between where the first two colors were? What does it mean to neutralize something?
Against each other, it's like positive.
So, Switzerland was neutral in the Second World War. Were they working against anybody?
No.
What is this quotation mark with your finger
They
thing?
were neutral.
On an official capacity.
They were Nazi.
So on an official capacity, they were neither for the aggressors nor against the aggressors. They existed somewhere in between, even though a lot of Swiss people were involved in the underground resistance.
Yeah.
Did you know that to this day, in the Vatican City,
They still have all the Nazi gold.
all the bodyguards for the Pope are Swiss, because Switzerland is neutral. And if you take a look and you see the soldiers that are on duty, they're in their traditional Swiss costumes, military costumes from way back then. So it's pretty colorful. So neutral means neither acidic nor basic. In some of the cases, you didn't quite get that, because neutral on the pH scale is a 7.
The Swiss also still have all the Nazi gold.
Pardon me?
The Swiss still have all the Nazi gold.
Really? I didn't realize that.
They got very, very rich off the Nazis. That's why I said they're neutral.
So there was a lot of financial gain off of this.
They held it, and then the Nazis dissolved so nobody could claim it. So they kept it.
Oh, of course.
And they allowed the Nazis to go through their land.
No Nazi came to claim it, so
Yeah, so they just kept it.
Is that why the Swiss
Yeah,
bank
please stop that.
is such a powerhouse in the financial world, and you can invest in or deposit money in the Swiss bank and nobody can find out what you've done? Okay, that makes some sense. Thank you. I learned a little bit of history today. So neutralization means that the substance that is formed is neither an acid nor a base. It's neutral. If I have sodium hydroxide and hydrochloric acid, I can predict the chemical products using the rules that we learned before the break. And essentially, you're forming salt water. Salt itself is neither acidic nor basic. Pure water is neither acidic or basic. The reason why your color changed when you added these two things together was because they were basically canceling each other out. If you ended up in the orange range after you combined them together, that meant that there was still leftover acid. Not all of the acid was neutralized because there was less base than there was acid. In order to get complete neutralization, you have to start with equal concentrations and amounts of sodium hydroxide and hydrochloric acid in order to cancel them out. There are several things that we use in day-to-day life that can be placed on the pH scale. We talked about battery acid being in around the pH of 2 last day. Lemon juice. We often add this to water, or sometimes we make a tea with hot lemon and honey in order to help with the sore throat. That's in around the pH of 2 or pH of 3 range. If you use vinegar in a salad dressing, or if you put it on fish and chips, for example, that is acidic. It's not as acidic as battery acid, which is a good thing. You wouldn't want to be consuming food and damaging your esophagus at the same time. Nope. It says that it's a little bit acidic, but it can depend on how close it is to the expiration date. Have you ever accidentally drank milk that's turned?
Yeah.
It's pretty sour, it's pretty gross. It's more acidic than a pH of approximately 6.5. Once you get into the basic range, you can use things like baking soda. Baking soda is an excellent neutralizer. I often will neutralize an acid that you have used in the lab by adding baking soda to it. Have you ever heard of milk of magnesia? It's an old name, but you might have taken something that's very similar. Tums? For an upset stomach, usually you've had too much to eat, and the stomach has produced a lot of acid to try to digest all the extra food that you've eaten, and it creates an uncomfortable burning sensation. So consuming milk of magnesia or Tums will decrease the acidity by increasing the pH. It is possible to consume too much Tums or milk of magnesia and neutralize your stomach. If you do that, you're probably going to have a very upset stomach because it's not going to break down the food very well. And then that food is going to have to make its way through the small and large intestine, and it's not really prepared very well to go through there. Do any of you use ammonia for cleaning, for example? It's quite basic, pH of 12. This is the same stuff that we use for fertilizer as well. You'll often see tanks of it just kind of in an enclosed area in the middle of nowhere. Think about when you go south past the North Quay corner. There's an ammonia drop-off area there where farmers can go and fill up. Have you ever noticed that there is a cone flag? A cone flag. You'll often see them at an airport because pilots need to know which way the wind is going. So it's a flag.
All those things.
Kind of looks like that. So it catches the wind and it sticks straight out. So you can very clearly see the wind direction. Why would that be at an ammonia site? Any guesses? It is.
It's like if it blows a certain way, it could like harm people.
It is so basic that when it hits the mucous membranes, the eyes, the inside of the nose, the inside of the mouth, it burns. If you inhale, well, you've got all nice moist tissue all the way down into your lungs, it will actually burn the inside of the lungs all the way down and will actually damage lung tissue. So if there's some kind of leak, they have to know who's downwind, because that's where they need to coordinate. First aid response is downwind. The people upwind are safe, but the people downwind are not. One time I was in Red Deer when a train overturned and an ammonia tank burst open. I was in a shopping mall where somebody spilled perm solution or something. And no, it was this tanker, and we had to evacuate the north side of Red Deer. It was hard to breathe.
If it's so harmful for people, why are we putting it on our food?
Because it dramatically increases the yield of the crop. And by increasing the yield, we make more money and we can feed more people. But it's not without its dangers. Have to be very, very careful when you use it. Lye is pure sodium hydroxide. This is actually what you were using yesterday and on Monday, except for it was mixed with water, so it was very dilute. we have special rules for naming acids. I would actually recommend that you put this set of notes on your table. Acids are very interesting compounds. When they are pure substances, they tend to act like molecular compounds. However, when you add them to water, they act like ions. We have a different way of naming them because they don't fit completely into the ionic compound category or the molecular compound category. There's 3 rules, and it's all about what the original name ends with. If the original name ends with IDE, we take the root word of the non-metal and we put it in the blank. Right here. You used hydrochloric acid yesterday. The original name for that is hydrogen chloride. So we take the hydro part of the name, and that's what we start with. Then we take the root word without the IDE ending, and that goes here. The next 2 names don't use hydro at all in their acid name.
Can you go back one time, please?
If you turn over your periodic table to look at the polyatomic ion chart in the back, notice that there are a few things on that back side that have ATE endings. I don't know if you want to highlight those and indicate that they fit into rule number 2. If it is an ATE, we totally knock off all of hydrogen. We take off the ATE ending. Whatever comes before ATE goes into the name. Sometimes we have to add a couple of letters to make the word make sense. So something like sulfic acid doesn't sound right, versus something like sulfuric acid is a lot easier to work with. Rachel, can you please go back to your station? Thank you. This one takes a little bit of practice to figure out what letters might need to be included in the name and which ones might not need to be included in the name. The last category deals with the substances that use the ITE rule. Again, these are all things that come off the polyatomic ion table. If you take a look, pretty much anything that you didn't highlight for an ATE is 50-60% ITE. Again, hydrogen completely disappears from the name. we use the root word of the ion name, and we add in the OUS. As with anything, we need to practice. You had a worksheet on your desk or lab station when you came in titled Naming Acids Worksheet. Does nitric acid fit into rule 1, 2, or 3? No. Is there a hydro on the front of it? So rule 1 would have hydronitric. So the first one, nitric acid, doesn't fit into rule 1. Does it fit into rule 2 or rule 3? It's this one. So you need to take nitric acid and translate it into a formula. To do that, you need to go backwards from nitric acid to hydrogen nitrate. See if you can come up with the formula. Good. Yeah, definitely. You're using the back of the table. Anything with an ATE or ITE ending is going to come from the back of the periodic table. Awesome. So, nitric acid is HNO3. Hydrocyanic acid. Does that fit into rule 1, rule 2, or rule 3? Has the prefix hydro on there. Only rule 1 has an acid name that has the prefix hydro. That means if we work backwards, hydrocyanic acid becomes hydrogen cyanide. Now, I'll give you a hint. This is one of the few IDEs that comes from the polyatomic ion table. The formula for hydrocyanic acid is HCN. Chloric acid. This is rule 1 or rule 2 because it's got an IC ending. It's got to be 2 because there's no hydro. If we go to here, chloric acid goes back to hydrogen chlorate. Remember, if it's an ATE, it's got to come off the back side. Keep working through this worksheet.